Hello.
Hello.
Yeah,
Sir, good
am I
evening, sir.
audible? Good evening. Good
Yes, sir.
evening.
Yes, sir.
Hello.
You are very much audible.
Okay, let me also check my camera.
Okay.
Just give me. So, is my video also visible?
Sir, your audio is little disturbed.
Okay, so let me check. Is it better now?
Yes, sir. Yes.
Okay, good. In terms of video, is this
Yes, sir. Video is clear. Yes,
this
sir.
clear? Okay.
Yes, sir. Yes.
Okay,
Yes,
good.
clear.
Okay, yeah, good. Thank you. So I think we set up. Let me also share my slides.
Okay. Sir, let us wait for 5 to 10 minutes.
Okay,
We
sure.
have around 90 plus faculty members around the nation,
Okay, okay.
participating in this FDP. Might be in
Okay.
evening time, they'll be slowing, then it'll, and the meeting gets populated by 6:30 around. Slowly
Okay.
it'll.
Okay, no issues. I have
Uh,
kept the material light and also I'll go a little slow. So
yes, sir, please.
you can. But we have to end by 7:30, right? Because you have the next FDP at
Yes, sir,
7.
yes, sir, yes.
And how is usually like, is it interactive or do we have questions at the end?
We can interact. We can stop
So
the
maybe in
presentation in
between some
between.
places, I will have some pause in case someone has questions.
Yes, sir. Yes.
Something. Okay, good. And do you record this? How does it go?
Yes, sir, we'll record. And
Sure.
as per ATAL norms, we have to share the recorded links and presentation. The presentation should be shared with the participants for them to prepare for the test at the end of the
Okay.
FDP to get the certification.
Okay, got it. Just give me a minute.
Yes, sir, please.
Just be back.
Okay, sir.
So current participants are from Adi Shankar College or the externals one also have joined?
The external, sir, we have
Okay.
90,
No, no. So
110
those who are
plus.
joined currently, they are also external participants.
Yes, we have some external faculty
Okay.
members also joined.
Okay. So people are joining already. Okay,
Yes,
good.
sir.
Yeah. So yeah, good evening to everyone and welcome to this.
So let us wait for some more minutes
Sure, sure.
for all the participants to join. So we are sending the reminders in the WhatsApp group.
Okay. So just wanted to confirm, is my slides visible?
Yes, sir. It's visible.
Okay, okay.
Sir, sorry. Let us wait for 3 more minutes. We shall start by 6:05. Is that fine, sir?
Yeah, no issues.
Okay.
So
Okay.
I joined from another device just in case of any network issues.
Okay. Okay. Sir.
Ma'am, shall we start, ma'am?
Yes. Let us
Okay.
check. Sir is ready now.
Yes, ma'am.
Yeah, I'm ready. So no
Okay,
issues.
sir. Then we shall start.
Okay.
Good evening, everyone. We now begin the first technical session of the fourth day of the 6-day ATAL-sponsored online faculty development program on advancements in cloud and edge computing, research and industry perspectives, organized by the Department of Computer Science and Engineering, Adi Shankara Institute of Engineering and Technology. The first session of the day focuses on an emerging and impactful topic, edge computing, which plays a crucial role in enabling low latency, real-time data processing and intelligent decision-making closer to data sources. It is my privilege to introduce our first resource person for the day, Dr. Rajesh Kedia, Assistant Professor in the Department of Computer Science and Engineering at Indian Institute of Technology, Hyderabad. Sir brings with him strong academic and research expertise in distributed systems and next-generation computing paradigms. His session will provide valuable theoretical insights and practical perspectives on edge computing for research and real-world applications. Sir, we are honored to have you with us today. I kindly invite you to take over the session and share your expertise on edge computing. Thank you, and over to you, sir.
Thank you very much, Parvati, and I'm also thankful to Dr. Ramani and the entire team of Adi Shankar Institute for coordinating this FDP and for inviting me to be a speaker in this one. So thank you very much, and I'm also happy to welcome all the participants who are doing this FDP for this session. So as I understand, today we have two sessions, one on edge computing and the other one following this on the fog computing. Okay. So let's okay, so this will be the outline of my today's talk. So what we will do is we'll quickly go through what is edge computing, where we need it and why we need it. And then I'll give you about perspective of what are the challenges with edge computing. Specifically, I will look into some details of how AI/ML workloads can be executed on edge computing and what could be some of the changes, some of the advances that would be helping that. Then I will give a brief idea of what are recent advances in edge computing, and then towards the end, we'll keep a small discussion where you can share your questions or any other opinions, and we could discuss about this. And in between as well, I will pause at certain points. So in case there is any question, you did not wait till the end. We could interact as and when necessary. So let's look at how computing evolved over the last 4 to 5 decades. So what we used to have at some point in time was mainframes where computing was centralized. People used to go work on those systems, and that's used to be the era of mainframes. But after that, we entered into the era of personal computers where everyone used to have their own computer at their home. Right. So this it was a desktop system earlier, and then gradually we had laptops. But this is all what gets classified as personal computers, where everyone had their own computers. We used to do computing, and there was a very limited requirement of having connectivity. A lot of things used to be at the individual's end. And then internet came, and then we connected all these computers, but still computing remained confined to local computers for a long time. Even though internet was popular, a lot of computing used to happen on local systems. And then in the last 1 decade or a little bit more, what we have is the cloud computing, where we can offload a lot of computations to cloud service providers through easy access because of a lot of advances in networking as well as other advances. Cloud computing started catching up. Right? So one of the biggest advantage it provided was you don't need to invest in any of the infrastructure at your end. Even if you have simple devices, you can do much larger scale computing through cloud. And then what we have as the topic of this FDP, as well as what we'll be talking today, is that now we also want what is called as edge computing. So cloud is there, cloud is evolving and helping, but it's not sufficient alone. We also need edge computing, right? And what is this? We will talk about in the next slides. So again, what we have is we have evolved from a personal computing, we went to the cloud computing, but then we identified that it has certain limitations, and then we come up with what we call as edge computing. And we would like to see what it is and what are the benefits and challenges that it comes with. So what is edge computing? Right. So again, the name itself. So what is edge computing is that rather than sending your computation to cloud, right? So when you ask any computation to be done on the cloud, you also need to share data. And we don't want to share data for various reasons. So what we want to do is we would like to bring the processing closer to wherever the data is generated, right? So we don't want to use cloud. We don't want to send our data to the cloud, but we would like to do the processing at the place where the data is generated, or to give more details, it could be processing the data either on the same device where the data is generated. Now, how is data generated? Data could be generated through various sensors that we have, right? So we have camera, we have uh, location sensor, we have many other kind of sensors that we have. So data gets generated on these sensors, on these devices. And rather than sending this data to cloud for doing the processing, we are saying that we would do the computation or processing on the same device where it is generated. Or maybe if my device is not capable of handling such computations, I can process them on a nearby local server, right? Again, when I say local server, there is something which is accessible only to us or maybe only to a limited trusted set of people. And it is not something that is a cloud being offered through a unknown service provider, or it could be something which is a nearby edge gateway. So whatever it is, in summary, what we are saying is we need to bring data processing closer to the device where, or closer to where it is generated, and it could be processed either on the same device or on a local server or nearby edge gateway. We'll see some examples of these. Or in a way, we can say edge computing means processing without sending to the cloud. So when we say without sending to cloud, it means we are processing in the premises where the data itself is generated, right? So that is how we can define edge computing. We can say what edge computing is, right? Now coming to the next part of it, which is why we need edge computing. Why would we need edge computing? Maybe I can also ask some participants to just type. Are they allowed to type?
Yes, sir.
Yeah, so maybe you can just share some points. Why do you think we would require edge computing? So we have a good number of participants, I see 40 plus. Maybe anyone would like to share why would you need edge computing? If cloud is available, why not send it to the cloud? Why would you like to do any processing local?
Sir, it can be of two reasons. One is of security,
Okay.
sending a data to cloud, and other can be like for certain scenarios we need quick responses rather than to avoid the latency.
Yes. So there are multiple reasons. I think the two most important reasons you have summarized. So one thing is that a lot of data could be sensitive data or private data which you don't want to send to the cloud. And the reason we are concerned about is we don't know where the cloud is, who is owning the cloud, and how the data gets used. Right. So that's one thing. So privacy is one of the important reasons why we would like to do processing in the edge, because if it is my data, I don't want it to go out anywhere. And then the second thing why one would like to do processing on the edge or near the data where it is generated is if you access cloud, it is through internet, it is through some network, and it is not always reliable. It is not always guaranteed to be available. What if you have more delay in the network? What if the cloud server itself is very slow due to a lot of load on that server? So there could be multiple reasons where you cannot guarantee that you will always get a response in limited time. And certain applications would require that you get the result, get the processing done in a given time constraint, right? So there could be this also is another important reason. So why would we need time? So we can call them as privacy is one of the reason, as I said, and latency is another reason why you would like to do computing on the edge rather than going on the cloud, right? Uh, so these two being important reasons, there are certain other aspects that are there. So reliability, right? So as we said, what if there is no network at certain place? So you are having some device which you are taking in different places. For whatever reason, if there is a network outage or you are in a location where the network is not available, then do you just not do the computing, or do you want to have something which can work, right? So that's something again where you would expect that reliability is available to you. Now, what could be those systems where you would expect better reliability? We'll see in subsequent slides. Scalability is another very important aspect why edge computing could be useful, right? So what do we mean by scalability is, let's say you have built a system today, you have something that works well for 100 users, right? And tomorrow you want 1 million users, you want to scale it to 1 million users. And if you have designed the system to just be working on cloud, and if you are not able to scale the services to that quantity, then you will find that while it was working well for 100 users, it's not working for the large number of users, right? But if you have edge computing where every user has a device in their near local premises and they are able to do the computing, then even if your number of users increase, as long as each of them have their device, the system is scalable, right? So that way, scalability is another added advantage that is provided by edge computing, which is not provided natively in a cloud-based system or any other similar system, right? Now, there is another aspect that we look at, which is cost. Now, cost, I put a question mark because cost slightly depends upon the cost of the device as well as the cost of the cloud services. Now, with edge computing, one advantage is once you have paid for the device, once you have bought the device, then you may not need to pay any recurring cost, right? Whereas with cloud, if you have some subscription model or if you have to pay per usage charges, then the charges may be higher. So again, cost is, we cannot say that it is better in edge or it is better in cloud because it depends on how many such computations you are doing, how frequently you need to go to the cloud, and what is the device cost versus what is the cost. But cost is also something that can be one of the factor to be considered when we are saying why one would need an edge computing, right? So these are different reasons why we would like to go for edge computing. Now, what are the kind of applications where you think edge computing matters? Does edge computing matters when you have to do weather prediction? No, right? Because those are not the things where you are concerned about privacy or you would like to do them without going to the cloud. And so there's certain applications where you don't need to worry about the factors that we mentioned. So in those cases, we cannot or we would generally not like to go for edge computing, right? So for example, doing some scientific computations, let's say you are running MATLAB simulations, you are running any others evaluation tools simulation, those places you won't go for edge computing. Now, where are requirements? What are the applications? What are the scenarios where one would like to use edge computing? So one of the very important place which is being talked a lot about in today's world is healthcare, right? And when we say healthcare, it is both health monitoring as well as treatment. So depending upon the medical conditions, sometimes doctors put wearable sense. Sorry, is there a question? Okay, so sometimes the doctors put some sensors, some kind of devices on patients so that you can keep on continuous monitoring of the health. And in case there is any anomaly detected, then you can maybe alert the doctor or you can alert any uh, relatives or any caretaker of the patient, right? So that's one place where a lot of data is continuously being gathered by the system and analyzed. Now, there are two options. One is you can send the data to cloud and analyze, but then as we said, it is not always reliable. And also medical data is very private, very sensitive data. We don't want it to be sent to the cloud. Right. So what we would like to do is we have some device nearby, either the same device that is the patient is wearing, or maybe the uh, some other gateway at the home where we could do this computation without sending the data to the cloud, right? That's one part of it, whether health monitoring or diagnostics, where we could use edge computing in healthcare. Also, nowadays, people there are a lot of treatments that are happening through electronics, and for example, there's robotic surgery. There are some other things that are happening where you would require a lot of computation and you don't want to depend upon any external cloud or anything, right? So you would like to have the entire system ready and available to you in your own premises. So even for those kind of situations, we would like to use edge computing, right? So edge computing is important in healthcare, and more and more with more and more advances in healthcare technologies, the dependence of people on electronic devices is increasing, and that's becoming more and more important. The next place where edge computing could be useful is autonomous systems, which could be vehicles or drones or any other equivalent systems. And what could happen is, let's say you have an autonomous car and which is moving from one place to another, and it needs to what is it that it needs to do? It needs to continuously keep on sensing what is there around the
Hello.
Hello.
I think there is an interruption at resource. Let me
I'll
check with him.
Okay, ma'am.
I don't know.
Okay. So in those cases, so what happens is a lot of computation goes on in the system. And again, if you put all those computations to cloud, and let's say the vehicle is moving in a region where there is no connectivity, then suddenly your system will stop working, right? So you cannot rely on those kind of systems if it is entirely dependent upon the cloud. So you should have a capability to moving from one region to other, it should be able to do the processing on its own, right? So otherwise, what will happen is you are sending a drone from, or even if you are flying a drone due to some internet issues, it will stop working. So we don't want these autonomous systems to be affected by network-related disturbances, and that's where there is a need to have local processing capability into these systems. Industrial setup, a lot of with advances in automation, lot of things in industrial premises have been moved to electronic based control. And for example, manufacturing houses, a lot of things are taken care automatically by electronics, right? Or even surveillance, where you want to see whether something going wrong or there is some kind of an action, some kind of an activity which requires immediate attention. So in those cases, again, you cannot rely on an external cloud. Maybe you also don't want to reveal those data to the external cloud. So again, all the concerns that we talked of, privacy as well as latency of action, this applies to here as well. And we would like to have a system which can do processing in the premises without sending it to the outside. Right? Now, one difference that comes between autonomous systems that we are talking of versus the industrial setup is that autonomous systems are moving from one place to other. Right. So here you cannot even rely on having, let's say, in the industrial setup, you can say that I will have one local computer system or a small server or something which can actually do the computation. Right. So you can say that my device or my computation system at least involves some local PC, but in case of vehicles and drones, you cannot afford them because these are moving systems. So whatever you have, you should have within the device or within the vehicle itself, right? So that's another difference that comes when we are talking of different kind of edge computing scenarios. So autonomous systems, because they are mobile and moving from one place to another, whatever edge computing facility we are looking at, it should be available within the system itself. Then we have a lot of things, different initiatives at the government level and at the even at the local body level, where we are talking of making a lot of cities as smart cities, where the traffic is managed in a smart manner, the emergency is handled in a manner where it is automated or involves a lot of electronic and digital decision making. So there also, again, we cannot afford to have things which are left to some unreliable situations due to networks or due to unavailability of the cloud, right? So let's say you have built up a traffic management system which relies on the cloud, and for whatever reason there is a cloud outage, right? So the service provider, whoever it is, there is an outage at their end, and even if that outage is for 10 minutes, it can lead to a big chaos in the whole city. right? Or if there is an emergency that you want to attend, but due to the outage at the cloud level, you are not able to attend to it, or you delayed the emergency by even 15 minutes, it can turn fatal for someone. Right? So in all those situations, again, we would require to have some kind of a processing in the local premises, which can be something which is under our own control and is not affected by external factors. Right? Then there are many examples I can go up. I just picked up some few examples. So there is also a lot of AR VR systems now used for education, used for many other purpose, entertainment purpose, etc. Now in these AR VR systems, the whole purpose or the whole baseline is that we get a feeling of reality because of the speed at which they operate, the frame rates that they support. Now just imagine that due to network delays, you are going through an AR/VR system which lags and which is the frames are moving slowly. In those cases, what will happen is you will not get the actual intended feeling that you are supposed to get from such system, right? So these also, because these are generally this cost a lot, so you would not like to spend money and then leave things to chance or leave things to network situations. So you again would like to have a local or an edge computing setup in these kind of situations. Right? So again, just to summarize, so what we have is we have edge computing requirements in many applications like healthcare, autonomous systems, industrial setup, smart cities, AI/VR systems, and many more. But it doesn't mean that edge computing is needed everywhere. So as we said, in scientific computing, in weather prediction, in DNA simulations, in a lot of this medical development where you are discovering new drugs and all. So all those kind of places can applications can still work on the conventional cloud or data centers or large supercomputers. But a lot of applications where human being is involved directly and where we need an action in a given time is where we would like to have edge computing supported. Now, coming to what kind of devices we could have, which are considered for edge computing. Would we consider a big supercomputer for edge computing? No, right? Because neither we would be able to afford it in our local homes, nor it would be something that can scale to a larger number of devices. Right? So, what are the various edge computing devices that we have? So, there are a lot of these small IoT devices. For example, the sensors that you have, something that is sensing the temperature of the room, something that is sensing how many people are there, maybe the cameras which are there. All these wearable, which I mentioned, are mounted on patient's body to monitor different behavior or monitor different parameters of the health. So all of these could themselves be edge computing devices. So they can have small microcontroller kind of a CPU which can do a little bit of a computing. There could be small memory, there could be some small support that they could have. So these could be some devices which could do some first level of computing, right? They may or may not always be able to do very complex processing, but some initial level of processing can be done on these devices. And if the overall processing requirement is simple, then these devices could themselves be the edge computing devices. If not these, then we can also have some smartphone where all of these devices connect to, and then they can use these smartphones to do the computing. Right? So as we know, today we have smartphones where we have multi-core processor. We have slightly better processors than what we have available in these sensors, cameras, and wearables. So one could use with all of these sensors, cameras can connect to smartphones. Now, this connection is much more reliable because this is a connection within the same premises. You can use, you need not use internet, Wi-Fi, maybe you can use some technologies which are more reliable, right? And you can have smartphone or tablets or any other equivalent kind of devices which are more powerful than these IoT devices, and they can support processing the data received from different sensors. The other kind of devices which can also help do the computing is a lot of we have routers in our homes or in the premises, and we may have other network devices. So all of these devices also have some processor and some processing capability. So if we don't want to use smartphones, all of these small IoT devices can connect to each other through these routers, and they can use these routers computing capability to do the processing. So this is also one more place where you could do edge computing. Or, as I said earlier, you could have some simple PC in your premise, some small, again, you don't say that we have a very high-end data center, but we can have a simple PC, or if it is vehicles already have a lot of processors inside them to do a lot of electronic system handling. So we can use those processors, or in the drones, we could have some processors. So all of these can also be used to do edge computing. And again, these are some examples. Based on some application, you can have one or more combinations of this, or just one of these being used to do edge computing, right? Now, what are the limitations of such devices, right? So one of the biggest limitation or difference from the cloud systems is these edge devices use simple processors, right? Unlike cloud systems, which might use the latest and the most advanced processors, these edge devices use simple processors, simple CPUs, which are generally embedded CPUs, and they follow what is called as RISC instructions, reduced instruction set computer. Again, we'll not go into details, but these are simple instructions, and they can the reason why we have these constructions is because they are simpler to implement, simpler to design, and consume less power. Right? Compared to the high performance CPUs, so in the cloud we will have CPUs like Intel CPUs, or in the server grade very high end CPUs from Intel or AMD or from any other equivalent companies. Whereas when we talk of embedded CPUs, we could have simple ARM. One of the popular companies ARM. We also have what is called as a RISC-V, and maybe many other embedded systems CPUs could be there. Right? So they are limited in their compute capability, but they consume much less power, or they come at a much lower cost than the cloud grade CPUs. Also, when we compare the number of cores that we have, so on a embedded on a edge device, we will also one core, or maybe a single small number of core, right? So generally you will have many of the devices will have only one core, but you can have otherwise two or four or up to eight cores, right? You won't find a edge device where you have 32 cores or you have 64 cores. But when you talk about cloud and all, you can have any number of cores much larger than what you have in these edge devices, right? So one of the biggest comparison or limitation of edge devices compared to cloud is that they use simple processor, and when we say simple processor, they take more time to do the same job compared to what the cloud would take. And also they are limited in terms of the frequency that they support. So the cloud processors can support much larger frequency in terms of gigahertz compared to what the edge devices can support. When it comes to memory, or what we also call as RAM, the edge devices are heavily limited. Some of them, like the sensors and all, might have kilobytes or megabytes of memory. Whereas when we talk about the smartphones or routers, they may have a 2 GB or 4 GB or 8 GB of memory. You won't find edge devices which have 64 GB memory or something like that. But again, when it comes to clouds or servers, you'll find much larger amount of memory that is available. Right? So when you have larger memory, how does it affect computation? The If you have larger memory, you can actually handle much larger amount of data. You can do much more complex processing than what you can do in these edge devices. On similar lines, the amount of available storage is also less on edge devices. So how is this memory and storage different? So memory refers to RAM, whereas storage refers to your hard disk, or storage refers to your flash or NVM, which is a non-volatile version where the data is not lost, right? So storage, for example, on your mobile phone, it would be generally like we would have 256 GB of storage. But on the small IoT sensors and all, you may have storage which is just a few megabytes or so. Right? Whereas when we compare the same thing to cloud, you will talk of TBs of storage, which is much, much larger than what you can have in the edge devices. Another biggest difference that comes is in terms of limited power or energy budget. Many of these IoT devices are powered by battery, and in that sense, they have very limited power. So they cannot keep on doing a lot of computations if it consumes a lot of power or energy. Right? So in that way also they are limited. So overall, there are multiple limitations, multiple reasons why edge devices cannot do all the processing that the cloud can do. And hence, there is a need to handle things differently for edge devices compared to just offloading things on the cloud. Right? But there is a need to do computation on the edge, and hence we must do something to enable processing on the edge. So with that, what we have done until now is we have discussed about what is edge computing, where edge computing can be used, and why do we need edge computing. And also we have discussed certain challenges with edge computing, essentially in terms of the devices which are available to perform edge computing. Right? So with that, I would like to take a small pause and open up for any questions that we have from the audience. So rather than delaying the questions till the end. So any questions from the audience or anything that was not clear, you would like to repeat the same? Okay, so if there are no questions, I'll move ahead. And yeah, if you want, you can also type your questions, and once in a while when we look at, we will be responding to them. So don't refrain from asking any questions, okay? Okay, so now the next topic that I will be covering is related to edge computing for AI ML workloads. Okay. Now, first of all, why do we need to do AI ML workloads on edge devices? Why not put them all on cloud? Because AI ML, the lot of applications which involve AI ML take inputs like images or healthcare data or location data of the user, which a lot of them are private, right? So, for example, if I'm taking a photo using my camera, you see that there are boxes drawn around faces and all, right? Now, when I'm taking these pictures, I don't want to keep on sending this to cloud because this may involve a lot of privacy. Everyone may not be comfortable sharing their images to the cloud. So what we would like to do is this kind of this box that is drawn around each of the face, or sometimes it is able to identify this screen where we are taking the picture, etc. These are done through ML techniques, but we would not like it to happen on the cloud, but rather on our own device. Right? So even images have a lot of personal and private. So we may take pictures from our house, and maybe someone is concerned about any kind of uh, if we share our images, maybe there could be some theft or something else, right? So there could be a lot of reasons why one may not want to reveal their images. So we would like to process them on the edge. And same is true for healthcare. We mentioned earlier as well. So a lot of health data is very personal to people, and you don't want to send that to the cloud services. So you would like to process them local. And again, a lot of these processing involves AI/ML based processing. Similarly for location and many other applications where you see AI/ML being used, but it involves private data. So that's the reason why we would like to do AI/ML on edge devices. Now, what is the challenge in doing it? For those who are aware of AI/ML techniques, they involve a lot of computations. Right? So don't worry if you don't know, but we'll not go into the details of AI/ML. But in general, these AI/ML applications, they involve a lot of computations, right? And also they use a lot of data. So for example, if you have to process images, if you are taking a photo or video and you want to process it through any of these techniques, it's a huge data with a lot of high resolution that we have. The amount of processing and the amount of data that we have to deal with is very high. Plus, there are real-time requirements, right? So we have a hard time limit. For example, as we said, in a healthcare, if there is any anomaly that is there, we cannot wait for the internet to be available and then process it. We may want to process it as within a given time frame. For example, anything that happens within 10 millisecond or within 1 second, we should be able to inform the doctor, right? So we may have some constraints like this. Or if I am taking a photo or video, I should be able to. So typically the videos work at 30 frames per second or 60 frames per second, right? So which means that if I have 30 frames per second, I have only 33.3 milliseconds of time available to me to do the processing. And in many cases, it may happen that network delay is much larger. So in those cases as well, we would like to avoid depending on the external network or external cloud and do the processing uh, in a controlled setup which is available to me as an edge devices. Right? So these are reasons why we would like to, even if we look at other applications, for example, you have a vehicle that is moving and it is sensing the environment through cameras and making a decision on whether to apply brakes or not, right? So based on some of these ML algorithms. Now, we don't want to depend upon an uncertain situation and be not able to apply the brakes or take an action within the given time, right? So those are again some systems where we would have a very strong real-time requirements. And to meet these real-time requirements, we have to have something which is reliable even if we don't have a connectivity to the internet, right? So these are some reasons why I would like to have AI/ML on the edge. And one very good thing about AI/ML workloads, and that is something that has been exploited a lot by developers, designers, is that many of these AI/ML applications don't need 100% accuracy, right? For example, if I am doing a mathematical operation, I will always say that 5 plus 2, it should always give me 7, right? It cannot give me 6 sometimes, 8 sometimes. That's not acceptable. So that is the general computing requires a computation to be accurate. But when it comes to a lot of these AI/ML based applications, for example, if I have a picture and if I have 5 people in it, it is okay to have only 4 of them being identified. People don't mind so much if the fifth person who is little bit away from the picture not able to identify, right? So a lot of ML applications are inherently resilient to inaccuracy. Even if you do computations in a not accurate manner, these applications are able to do their job to some extent, right? So that's something which is there, which is what we call as an approximate computing or introducing approximation. And we'll see how some of these things have actually helped us improve the AI/ML execution of the edge devices. Right? So we'll see some examples of algorithmic advances, approximation, and hardware advances that has helped us achieve a efficient AI/ML execution on edge. Right? So by default, you may say that it works fine. You can run something on the device, but if it doesn't meet your time requirements, if it takes 5 seconds to just find to do some processing on a given image, then you will not be able to meet the real-time requirements like 33 milliseconds. Or in a case of a vehicle, you may have to take an action in within maybe 10 millisecond or even smaller unit of time, right? So what we want is we should be able to do processing efficiently in the given time on these edge devices. Coming to algorithmic advances, so there are many different ways to do AI and machine learning based processing. And things have evolved a lot in the past few years. In the earlier times, we used to have, for example, if you have to detect, given an image, if you have to detect a face inside it, there used to be some techniques based on image processing, right? So basically, you go through each of these one by one and find out certain aspects or certain features, and then there's a lot of algorithmic way of processing it, right? So you do this, do this, do this, like that. So those techniques used to be there, but they were not very accurate. They used to take a lot of time and were not very efficient to implement for edge. And then we came up with what is been used a lot in such image processing and image-based ML is what is called as CNNs, or convolutional neural networks, right? So what convolutional neural networks did is they converted this whole algorithm into some kind of a data-based processing. So you have all the image pixels being given to you as different inputs. You do some processing just to find out certain characteristics and generate some more values, or some what we call as features. Then you pass it on to different layers, and at the end, gradually what you do is you identify whether there is a face in this, whether there's an animal in this. So there are different kind of processing you can do to get different information about the given image, right? And it did not be image, it could be any other signal, any other kind of data as well, and you can identify certain useful features from that using CNNs, right? Now, what happened is there were a lot of CNNs that got developed, right? So some of these are for specific tasks, some of these can support many different tasks, right? Now, as an edge developer or as a system developer for the edge device, you can choose the one which meets your requirements, right? You need not always go for something that works. Something that works for one person may not work for another system that is being there. So based on what you have, there are many choices that are available in terms of which kind of algorithm or which kind of neural networks or what is the model that you want to use for AI or ML. Right? So they have been evolving, and with time, there have been models which are smaller and are able to give similar amount of accuracy as compared to older model. So there have been regular algorithmic advances. People have been trying to compress the model, reduce the model to smaller size, and without compromising on the overall accuracy or the performance of the model that we can achieve. And also there are many different variety of models. Some are very small models which can do some task uh, quickly, but at an approximate level. There are large models which can actually do things in much more precise manner, but they take more time, right? So now depending upon the system that one is developing, so if you want to run, for example, you want to run something on a sensing IoT device, right? Let's say you want to do something near the camera itself, then you can use a smaller model. But if you want to run the same thing on a mobile phone or any other better device, you can use a larger model. So depending upon where you want to run the algorithm, what is it that we want to achieve from the application, we can have different size of models, different kind of models that are there. And it is an interesting exercise to identify the right ML model to be used, right? You cannot just pick up something that is existing and saying that because someone else used it, I will also use it. No, it depends upon what is your application. So healthcare may require a different ML model versus a different application might require a different ML model, right? So that's also something that because we have different advances in algorithms, so we have come up with many different kind of models, which makes the choice large, but we can have things which are suited for particular kind of application. So similarly, we have other advances in various ML models. We have how so while CNNs are good at handling static data, There are time series networks which can, if you have something that is happening over time, right? For example, speech or something, where you cannot just say based on something that is there at one time, but overall across time, what is the words that you have spoken, all those things where you have these devices which can detect your command and take action based on what you are saying. So all of these are different networks that you may want to use. And then recently with advances in generative AI and all, so there are transformer models that are also there, which we could run on these edge devices. Again, that depends on where you would like to use it. But there are different models that can help achieve some of the AI ML applications on edge devices. Now coming to the kind of approximations that one could do. So why we do approximations? As I said, these AI ML models, they are not very specific about having exact computations, right? So they are okay to have some approximation, some inaccuracy in the processing if it saves the either it saves time or it reduces the requirement of memory or CPU to perform the computation. Right? So there are two popular kind of approximation techniques that exist in when we execute these AI ML workloads. So one of them is called pruning. Right? So what is pruning? So just to give you an example, so let's say I have a CNN model where I have a lot of inputs that are coming and I am generating many other inputs which are going to the next layer. This is what we call as layers. So layer one, layer two, layer three, like that we have different layers in a CNN. Right? So output of one layer goes as input to the next layer. Now what tuning says is that can we reduce some of these data? So can I eliminate some of these? Can I reduce a few of them? And is that okay? Is that acceptable for overall computing? Right? So that is what we call as tuning. We reduce the total number of parameters or total number of computation points that we have. Right? So if you look at it in details from another perspective, so CNNs can be modeled as some kind of matrices. Right? So again, how does that happen is not the focus of this course, but what internally the processing requires is you convert this CNN in some kind of matrix operations, right? So and you have one matrix and another matrix, and you do matrix multiplication, right? So that is the standard operation that is involved in a CNN. Now, if I can reduce the size of these matrix elements, let's say if it is n cross m matrix, if I can make it as n minus something, n minus p cross m minus q. If I can reduce the number of elements that are there in the matrix, it will automatically reduce the complexity of computations, right? So my number of computations will come down. So what will it do is it will reduce the number of metric multiplications that are involved. It will also reduce the storage or the memory requirements, right? Why? Because now I have less number of matrix elements to consider. So it also reduces the memory requirement. So it doesn't just reduce the number of computations, it also reduces the memory and storage, right? So that way, this is one very popular technique, pruning, used to reduce the number of parameters in the model. Now, what will happen if you reduce the number of parameters? You may be able to, you will see that the accuracy is dropping. Right? So as we said, if you do less, if you consider less parameters, you will see that the accuracy is dropping. But people have come up with very efficient way to find out which parameters to prune, and the accuracy drop, they are keeping it much less, something around less than 0.5% or maybe very small number, right? So that has been a lot of research in how can we do efficient pruning for these AI/ML workloads. And why we do pruning? We do pruning because by doing pruning, we can fit them on these edge devices, right? Otherwise, they would exceed the available memory. They would not be able to compute in the given time. But if I prune them, I reduce the overall complexity of the model. I can actually run them much faster, and I can fit them on the available memories of the edge devices, right? So that different works on tuning. One of the very popular approach, which actually is a very unique kind of tuning, was mobile net, where people said that earlier we were not able to execute neural networks on mobile phones, and by doing such kind of structured tuning, we were able to reduce the we were able to fit the mobile CNNs on mobile phones. Right? So that's one thing. There are many other works on pruning. Now, what can you prune? You can prune the number of parameters at each level. And sometimes people say we can also prune the layer. Why to have multiple layers? Can we reduce the number of layers? That is also a possibility that is there. And that way, there are many different things that one could prune, or basically, it's cutting down on the computation. The other way to simplify or reduce the overall computational load and make such AI/ML workload execute on these smaller devices is what is called as quantization, right? What does quantization mean? Quantization means that you reduce the width of each parameter, right? So in pruning, we are saying we will reduce the number of parameters. But now in quantization, we are saying let the number of parameters be the same, but can I reduce the complexity of each parameter? Right. So for example, if I have each parameter in the original design as 32-bit parameter, can I reduce them to 8-bit parameter? Or can I reduce them to 16-bit parameter? Right? So how will this help? Any thoughts? How will reducing 32-bit to 8-bit or 16-bit help? I will still have that many number of parameters. I will still have to do that many number of computations. But what is the benefit of reducing the width of the parameter? So,
Time saving.
sorry?
Time saving. I quick
But
process it.
why
That's the
will it
number
save
of
time?
bits are
So the
reduced.
question is, why will it save time? Instead of 32-bit, if I use 8-bit, why will it save time?
See, everybody needs a quick response, right? That's why.
Yeah. So basically when we reduce 32-bit to 8-bit, what we can do is we can use simpler hardware. We don't need a complex hardware. We can have small adders, small multipliers which can handle 8-bit. Or if I have, instead of 32-bit, if I have 8-bit data, so we have something called as vector processing in our CPUs, where you can process multiple things in parallel. Right? Now, if I have 32-bit parameters, I can process only limited number of things in parallel. But if I have 8 bits, I can have many more number of parallel processing that is possible. Right? So that is one benefit that you get by reducing from 32-bit to 16-bit or 8-bit. The computation hardware becomes much simpler. You can do more amount of parallel processing if the hardware allows it. The other benefit you get by reducing from 32-bit to 8-bit is your memory requirements come down. Even though we are not reducing the number of parameters, but because we are reducing so a 32-bit parameter will require 4 bytes of memory, whereas a 8-bit parameter will require only 1 byte of memory. Right? So if you have 1000 parameters, in the earlier case, you'll spend 4000 bytes. Now you'll spend only 1000 bytes. Right? So that way also your number of memory requirements also comes down. And as we have seen, memory is also limited in these edge devices. So by doing quantization, you can take care of memory issues as well as computation related issues. Right? So quantization is another technique. And both pruning and quantization are independent of each other. You can apply only pruning, you can apply only quantization, or you can apply both pruning and quantization. Right? So what you say is, I will reduce the number of width and as well as I will reduce the total number of parameters. So in that case also you can save and get benefits of both of these techniques. Right? So there are many more approximation techniques that are there. So this is a broad classification of what we call as approximation, or sometimes these are also called compression techniques. So what we are doing is we are compressing the model. We are reducing the overall size that the model will otherwise require. And by doing such kind of compression, we save on memory space. We also reduce the overall computation complexity that we have. Now coming to hardware support for AI/ML models, so there are many different kind of things. So it's not just that people have evolved over, people have improved only the algorithm, or they are trying to compress the models. But also from the other side, we are saying, can we have hardware support? Can we have hardware-based techniques which can help us execute AI/ML models better on edge devices? Right. So one of the very big change, big contribution from hardware for this is developing accelerators. Right. So what is an accelerator? Accelerator is a very specific hardware device which can execute or which can perform only the given kind of computation, right? So it's a very dedicated and a custom device for a given application. So what we do is we design accelerator for, let's say, for CNN, right? So we have an accelerator for CNN, which can execute CNN much faster and better than a general CPU, but it can do only CNN. It cannot do anything else, right? You cannot ask it to do anything else. But because people found that lot of edge devices require execution of AI ML models, they integrated CNN related accelerator into these hardware, right? So that's one very big inclusion in the edge device hardware is we have now many edge devices have CNN accelerators into them. And similarly, we also embedded GPUs. So as you would have already known that GPUs are very popular in ML execution. They are able to do a lot of things much efficiently for machine learning. But edge devices used to lack GPU, but with recent times, we have been able to have small, simpler GPUs which are available to these edge devices, which can be used to offload some of the ML computation to the edge devices. Right. So what we get by this is we get something which is not as complex as a cloud-based GPU, but something which can do things much better than using the simple CPUs that we have on these edge devices. Right. And we have also been trying to increase memory. So as you know, with technology improvements that is happening, memory size is increasing and the cost is coming down. So because of that, people have been adding more and more memory. Again, you can see as an example, the phones 2 years back used to have memory around 2 or 4 GB, but today they are having 8 or 12 GB of RAM available to them. Right, so that way we have been increasing memory, we have been increasing storage on the hardware devices that we have to execute the edge available at the edge, and with that we are able to support more complex execution. There's also been a lot of work on co-design of hardware and software. Right? So what does co-design means? You don't just design hardware alone and software separately. Can we design them together? Can we have hardware and software being designed together so that it is overall better? Right? And this is itself an interesting research problem. This is not a new problem. This is an old problem, but just that now we are talking of co-designing hardware and software for AI/ML. In the older time, people said co-designing hardware and software for image processing or for signal processing, speech processing. So application has been changing, but co-design is as such a problem that is there from old times, right? So what we are saying is, if I am building an accelerator, and let's say I come up with the best accelerator, but if my software is not able to use this, then what's the benefit I am going to get? Right? And vice versa, if I am having a software which is much efficient, but if I don't have a equivalent hardware, then what's the use of it? Now, if I can design them together, what will happen is I can make certain compromises in hardware, I can make certain compromises in software and come up with a very nice solution that works together for both. Okay. So that's another thing that has been happening. So with that, a lot of hardware vendors are providing their own software libraries which work much better on their hardware, and then we can use them to support various AI models. So these are things in terms of including hardware or doing the hardware design. There's also an equivalent and important aspect of now we are talking of all these edge devices. Many of them don't have just one core, but they have multiple cores, right? Now, when you have multiple cores, which task runs on which core is an important decision. You cannot keep on running everything on the same core, and you cannot keep just use the existing technology to use any one core to do whatever, right? So each core has certain differences. So now can we have better task mapping and can we do something which is aware of these models, which can actually help improve the overall time, overall power, and many other things, right? So this is something which is generally handled by a power task manager or the task to core mapper, which is available in the OS in general, or we can have our own custom drivers which can handle this. And then coming to a better use of the hardware knowledge. So let's say if I know that my system CPU has a given amount of cache, let's say if I know that it has 1 MB of cache, then can I use it in a better way? Can I change something in my overall model which works better, right? For example, if I know that I have a 1 MB of cache, then can I choose instead of choosing a so we said that we have models which could be small or large. So can I choose some model which fits better in 1 MB or which works better for 1 MB than something which is much larger or something that is much smaller, which is wasting my size, right? So if I have some knowledge of what I have in my hardware, I can make better decisions. And similarly, compiler can do a better job when it is generating the code. So if it has to run this matrix multiplication loop, it can partition it in a way that this we call this as a tiling. So it can partition the whole matrix into small sized tiles such that the tile that fits 1 MB better can be actually used. Right? So these are things that can be done along with the compilers. Or if we know that our hardware has some vector instructions or any specific instruction which can be more efficient than the standard code, the code compiler can generate those codes being aware of hardware knowledge and then use them better. Right? So these are again some of the things that goes along when you have to do better or efficient execution on the edge. If you just care about running something, that's a different thing. But if you want that things should run efficiently, then there are different things from hardware or from hardware plus compiler or from operating systems that could come in. Based on the knowledge of the hardware, they can do some better decision making. So with that, what we have seen is we have seen how we can run ML models better on edge devices. So we have different models. We can choose the right one as per our requirements. That's first thing. The other thing is we can introduce approximation or compression techniques, which can reduce the overall computation as well as reduce the memory requirements. Two very famous approaches towards that is what we call as pruning and quantization. And then we can also have a lot of hardware support, hardware-based techniques where we can have custom hardware for doing this processing, or we could have better memory, or we could have co-design of hardware and software, or we could use OS and compilers help to perform better ML model execution. So with that, what we have done until now, we have covered what is edge computing. We have seen what are the challenges with edge computing. And then we have seen some examples of how we can do edge computing for AI/ML on limited devices. Again, when I say edge computing for AI/ML, there are a lot of research that is happening where people are saying that can we run AI/ML on small devices as small as having 256 kilobytes of memory, right? Just imagine 256 kilobytes. Nothing very small. Even one small photo that I have, it will be 5 MB, right? So they are very small devices, but can I run even simple edge in AI/ML models? Can I just say whether there is a person present or not present? Can I just use it to do very simple checks and very simple automatic inferences? And people are saying, can I run AI/ML models on mobile devices? And mobile devices vary across range. So some very low-end mobiles have 2 GB or even smaller memory, whereas a high-end mobile can have 16 GB of memory, and even number of cores would be different in these devices. So when we say, can we run it on mobile devices, this itself is very large range, because different devices can have different amount of resources available to them. And this is a broader picture where we have AI/ML requirements on every small device, as well as we can have AI/ML being run on edge devices or gateway devices or network devices as well, right? So we can run AI/ML models on various kind of edge devices. Let's look at some of the new things that are there in the hardware or in other aspects which are helping in the overall edge computing. So there is something called heterogeneous cores that is there. So by default, when I say I have a multi-core system, let's say I have a processor with 4 cores, by default it means that all these 4 are similar kind of cores, right? But with recent times, what we have is we are starting to have a heterogeneous cores. So if I have 4 cores, 2 of them could be big cores, 2 of them could be small cores, right? How does this help? If I need a large compute capability, I will use the big cores. But in case I don't need it, I can use the small cores only, so that I can save on energy and power, right? I can shut down these big cores and you just use the little cores to do simple tasks, and that will save my energy and power, right? So energy is important. You don't want to keep on charging your mobile every time you do some computation or anything else. You don't want to consume unnecessarily a large amount of battery. So it is important to have such kind of a heterogeneous or mixed system. Whenever you need large, you use it, but if you don't need it, just shut it off and use smaller ones, right? So this is something that has happened. And a lot of edge devices are now, earlier, which used to be limited either on because they were consuming a lot of power, or because they were not able to do a lot of processing faster due to limited CPU capabilities, can now you are giving them best of the both, right? So they can do something. And having said that, this is available in ARM, and all the recent desktop systems and all that we have, there also we have. So instead of big and little, what we call them as performance cores. Anyone has heard of these terms?
Yes, sir.
Yeah. So nowadays, all these Intel, AMD, and all these CPUs, they have earlier they used to have 8 cores and all. Now you see they will have 20 cores. Right? Why 20 cores? Because out of this 20, only 4 are big cores. Rest all small cores. So we are able to afford a lot of small cores in the same cost that we would have otherwise just have had big cores, right? So all these heterogeneous systems are becoming more and more popular. Even the M1 chip or M2 chip from Apple, that also has something like this. They will have 4 performance cores, 4 efficient cores, right? So this is something that is happening and is available in all different edge devices as well. And then, as we said, we are adding more and more accelerators, which are for specific custom requirements. So we have neural processing unit, which can do CNN execution. We have image processing based accelerator, something which can process image very efficiently. Rather than doing it in a CPU in a general manner, we have a dedicated accelerators, or you can call them as specialists, right? So just like you have specialist who can do the same task much better than a general purpose person. Similarly, accelerators can do the same things in much better way. So we now, you will see that various devices have accelerators which can do CNN, which can do image, which can do video, because these are the requirements where you have a lot of computation, but you don't have enough processing power, right? So, and a lot of people are using these applications. So it makes sense to have dedicated accelerators to handle these kind of requirements. And as I said earlier, also memory capacity and speed both have been evolving and improving with time. There has been a lot of so one reason why we go for edge computing is we say that there is uh, issues in terms of dependability on the internet and all. So there are standards, there are 5G and other things which are improving connectivity, at least within the devices you have connectivity across the devices. So there are a lot of improvements coming in connectivity due to newer standards. And that also enables us to have dynamic edge versus cloud computing. Right? So we said that edge is needed. So if privacy is not a concern, let's say only latency is the concern, and somehow you know that the network is much better in a particular place. Let's say I'm in my home and I have a very good internet. So why not use cloud in those cases? So there is also option to have dynamic edge versus cloud. So you monitor the network speed and based on that you decide whether you want to send something to cloud or you want to do local computation on the edge. There is distributed edge computing where instead of having computing happening on one device, you have multiple devices at your home and you use all of them to do the computing. There's also something called fog computing, which is in between edge and cloud. You have some better trusted cloud, but that is not the actual cloud, which is the remote cloud, right? So you have something in your own premises, which is slightly better than the edge devices, but are trusted and connected with reliable network to the edge devices. And also something that has been helping a lot of edge computing is there has been a lot of improvement in battery and power management techniques that is helping us reduce the power consumption of processing on the edge. So that is also something that helps the edge computing, right? So some of these advances that has helped the edge computing, and one of the biggest advantage of edge computing is you can have many, many devices which are doing edge computing, which are doing the computation without affecting each other. So what you do in your premise has no connection to what I am doing in my premise. So we are not affecting each other, and we can easily scale if we have these many number of devices with us. Right? So these are some examples of advances in edge computing or advances in processing, in networks, in other things which are helping do better edge computing. And with that, we would like to quickly summarize the topic. So we have seen that edge computing involves computing things locally without going to cloud, and primary reasons for them are privacy, reliability, scalability, and latency. And these devices are typically limited in their available resources, which could be due to CPU limitation, memory limitation, battery limitation. And common edge devices are the mobile phone, the sensors, the network gateways, or some local processor or local PCs that we could have. Specifically for AI/ML, we have seen that there are a lot of algorithm or at approximation or hardware-based advances that could help us perform AI/ML based computation, but on local edge setup. And AI/ML, because it is becoming more and more popular, a lot of people want to use it, but it has a lot of computations and also some real-time requirements. So that's one of the focus area for today's world on edge computing. Having said that, it is not that we should only study or we should only consider AI/ML workloads. There are many other things which we could which could be used to which could be deployed on edge, and we have just taken AI/ML as an example. And there are other things that we just discussed. We are having better edge devices. We are also talking of things about edge plus cloud dynamic switching. and many other different kind of things which could actually. So the whole objective is to ensure privacy, to ensure the required latency is being met with a better with a better overall experience of using in the system, right? So it could be due to only edge, it could be due to edge plus cloud, it could be due to whatever are the other options that the developer has. So with that, I complete my this lecture on edge computing. The primary aim that I kept was I'll try to motivate and give you a perspective of what is edge computing, what are the things that are there in edge computing and all, so that you are aware of the terms, you are aware of some of these concepts, and it can help you explore more and more things on your own from the web. And also it will provide you a baseline so that you can understand the remaining part of the FDP better. So with that, I end my lecture. Any questions, I would be happy to take. I just project this screen as a small recap. So if there is any question, please let me know. You can type or you can speak up as well.
Dear participants, if you have any questions, you can use this time to pose it to sir, please.
Sir, in between, I had another question.
Yeah.
But the edge and cloud dynamic switching answered it. And I wish you to explore or say, give some light on tiny ML.
Okay.
How?
Yeah. Yeah, thanks, Dr. Mani. I wanted to speak about it. I spoke, but I didn't use this term, so that's a very good question. So tiny ML. So what is happening is, as we said, ML is becoming popular. A lot of people want to execute ML, and we want to execute ML on. So everyone knows that we can run them on cloud and high-end data centers. But what if we want to run them on very small devices, right? And what tiny could mean is, as I just mentioned, so tiny could mean that we are running it on a small device, which is a 256 KB device or something that might be in a small toy that a kid has or anything else, right? So tiny ML involves running ML in very tiny devices, right? And these devices are having very less amount of memory in terms of RAM as well as storage, right? So how do we actually run these ML models on such tiny devices? So one of the very important thing that we do is we do a lot of compression. We compress the model significantly, and we compromise on accuracy. Definitely, we don't say that we do it on a full accuracy level, but we compress the model a lot. We also consider this TinyML for situations where the images that we want to process or the inputs that we want to process could be of smaller resolution. Right? It's not a very high-end 1000 by 1000 resolution image, but it could be even as small as 28 by 28 or some 56 by 56 resolution image. Right? So there could be very small images. So this is one thing that we do. We compress the input, we compress the overall model to be processed. What we also do for such kind of tiny ML execution is we'll do a lot of optimizations on memory access pattern, and also something that I mentioned, if I have small memory, I would like to use it much more efficiently. So there are a lot of techniques that we deploy there to reduce this. So what I can suggest is there's a lot of work from MIT on this direction where they have a demo and they have the entire code on GitHub where they're running this small CNN models. So you can just search for MIT and TinyML. You will find a lot of resources. There are a lot of interesting research works on running ML models, CNNs, and even recently, I think, transformers on such very small devices. So that's there. So the main idea is bringing ML on tiny or smaller devices, and that is something which is TinyML is. So there's a lot of effort from various groups. So one of the very recent and popular is this from MIT. You can check that.
Hello.
Yes.
Good evening, sir. This is here said Bhavesh Kumar Sharma, Shada University, Greater Noida. Sir, I want to ask the questions. The actual difference in the real scenario, the difference between distributed computing versus fog computing, edge computing. What are the real differences, sir? Because, sir, I have used applications in the AWS. So I
Yeah,
am bit
see, edge computing, as I said, is computing at the edge, computing it within your local premises, right? Edge computing could be with only one computing device, or you could have more than one computing device. Distributed computing means you are doing computation with lot of different small, or maybe large number of servers, and you are distributing the task to them. So you have a large task, you distribute to different computers or different processing devices, and they together work to give you a result.
fog computing, sir.
Fog computing, as we said, comes in between cloud and edge. So in fog, what you could have is you could, let's say you have a better small, at your home, you have set up one server and now you are asking the server to process something. Or let's say you are in an institute where you have a smaller uh, trusted cloud which you have. You are not going to AWS or you are not going to any other external cloud, but you have a fog. I think fog you will get more clarity in the next lecture. So let me not take that surprise also from you. But when it comes, so about distributed computing, it is involving more than one computing devices, which could be on the server, which could be on the cloud, wherever it could be. But it is more like it's not restricted to your local premises, whereas edge is restricted to the local premises.
Okay, thank you, sir. Thank you, sir.
Thank you.
Sir, good evening, sir.
Yes.
What are the major key performance metrics used in evaluate the edge computing in especially research, sir? Key performance metrics used
Yeah,
in
so
edge
one of the key performance of edge computing is that the latency, right? So firstly, you should be able to meet your latency requirements. That's one thing, right? If you are not able to meet, so privacy is guaranteed by default because you are not sending the data outside, but you should be able to meet your latency requirements. And then there are other things, for example, power consumption. Are you consuming more power or less power? So that depends on the research topic. So generally, hardware designers would look at power and latency as metric. Maybe some other overall application developers could look at cost also as a metric to be considered, or how frequently you have to, let's say, charge your device. That also could be considered as another metric. So there are many different metrics depending upon who is actually uh, looking at that metric.
Okay, thank you, sir.
Yeah, thank you.
So personally, thank Dr. Meenakshi Madam no, for contacting you and facilitating this session possible with you, sir. Thank you so much. So before wind up, I'll have one quick question. Sir, agentic AI is now ruling the industry right now. Is there anything about no edge computing in that direction?
So I think here it's a very good point. So what can happen is, let's say, if I have a small agentic system, and if I deploy it on edge edge devices, and it can maybe decide that something that can be, so I mentioned this, we can use this edge plus cloud combination, right?
Yes.
So agentic AI can actually help it much easily, because then we can decide, okay, something which can be done locally And something that requires a lot of computation, much more complex problem, we can give it to the cloud. So I think those
Yeah.
kind of things could be integrated better.
Yes, sir. Yes, sir.
That's
Thank you.
a good point.
Yes, sir.
Thanks.
Thank you. Thanks.
And yeah, so if there's no more question, then I would like to thank the whole organizing team and all the participants as well for staying back till the end of the class. Thank you very much, and best of luck for the next sessions.
Thank you very much, sir. The session was truly insightful and beneficial to all of us. Thank you very much for delivering such an enlightening session. Good day to you, sir.
Thank you, and have a nice day. Bye.
Dear participants, we now move on to the second technical session of day 4 of the 6-day ATAL sponsored online faculty development program on advancements in cloud and edge computing, research and industry perspectives. The second session today focuses on a closely related and advanced topic, which is fog computing, which bridges the gap between cloud and edge by enabling efficient data processing, improved latency, and better resource management in distributed environments. It gives me great pleasure to introduce our second resource person for the day, Mr. Hitendra Saxena. He is lead technologist at Ernst & Young. Sir brings with him rich industry experience in cloud, fog, and emerging enterprise technologies. His industry-driven insights will help participants understand the practical implementation and real-world relevance of fog computing architectures. Sir, we are truly honored to have you with us. I kindly invite you to take over the session and share your expertise on fog computing. Thank you. Over to you, sir.
Thanks, Parvati. Good evening, everyone, and a very warm welcome to all of you. Thank you for joining today's session. And as I was told, and I can see there is a varied audience available right now from faculties, students across branches. And that makes this session relevant to today's world, basically for computing, right? Let me quickly introduce myself before we start. I am Hitendra Saxena. As mentioned, I am an associate director and a lead technologist in Ernst & Young. In my current role, I act as the global AI security lead in EY and emerging technology security leader in EY GDS as well. Over last 20 years, I have worked across multiple infrastructure, virtualization, cloud platforms, and the whole suite of distributed platforms and emerging technologies, enabling organizations in secure and scalable architectures. Right. Let me share my screen, and today's session is about, just give me a second. Can you guys see my screen? My system is restarted. Just give me a second. While it is coming up, basically, I'll just quickly give you a brief on that. Parvati, I'm not able to share the screen. Is the permission out there?
So let me just check with the admin team.
It's not allowing me to share my screen or the window.
Sir, it is possible with me. Um,
Ma'am,
Hmm.
can I just ask sir to send his PPT to us? Maybe Ambli ma'am
no,
can.
no, no. Sir, can you rejoin? Might be resetting your joining. Because, sir, hello. I think there is a network issue at his side. Hello, hello.
Sir,
Yes, there is a network issue at his side.
Am I audible, guys?
Yes, sir. Yes, sir. I think when you rejoin, you will be able to do that.
All right, let me try now. Okay. Hope you
Yes.
are able to see my screen now.
yes, sir. Your screen is visible now.
You are able to see the slides. Okay, great. Thank you. All right, sorry, I think that's a technical challenge that we had. But what I was saying is today's session is titled Fog Computing Technologies, Bridging Cloud and Edge for Real-Time Intelligent Systems, right? And as you see, the title itself, how modern systems actually make decisions in real time and why neither cloud nor edge alone is sufficient anymore, right? You have just completed this session on the edge computing out here, so this will be closely related to how edge, cloud and fog interrelate together in real world scenarios and in the industry as we talk about it. I'll be referring to the slides, diagrams and control on my main screen, so you might see me look away at times. That's simply to keep discussion clear and structured, right? More importantly, the session is conceptual and industry aligned. We'll not go into deep into coding. It's not coding heavy or it's not mathematical session. And you don't need any prior expertise in fog computing. If you understand cloud and IoT concepts, that is more than enough. Okay. I'll deliberately use simple analogies, real world examples, and practical industry scenarios. So whether you are teaching, researching, or working in industry, you can map these ideas to your own domains, right? We'll also have few live polls during the sessions, not to test you, but basically to understand who we have in audience and to make discussion more interactive. Before we move further, let's do a quick live poll. Okay. And what I would like to say is you put your responses on the chat if possible, and let me know about how have you worked with IoT, cloud, or edge system before. You have 4 options. There is no right or wrong answer here. It simply helps me calibrate the depth and examples that I'll be using during the session. So if you can quickly put in responses out here. All right, I see few responses coming in, D, academic knowledge, and all right. Okay. All right, so that's perfectly fine. And today's session is actually designed exactly for building the clarity on your conceptual and architectural level. Okay. And if you don't have any expertise, we will actually go step by step. So don't worry about any terminology if you're not across as well. Thanks for the responses. Now, this is the agenda that we will be covering today. As you can see, we will begin with why fog computing is needed, followed by a quick look at the evolution of computer paradigms that have evolved over time. Then we will cover fog fundamentals and architectures of fog computing. Then discuss about technologies that enable it and explore some real world use cases across multiple domains. And finally, we'll look at research challenges and some future trends, which should be particularly useful for faculty, research scholars before we open floor for questions. Okay, with that, let's get into the journey and let's get deep dive on to fog computing examples. Okay, now to understand fog computing, we first need to understand the problem it is trying to solve. We are living in a world where data is being generated everywhere. We have sensors, cameras, mobile devices, industrial machines, smart infrastructures, so many things, right? And application today demand real-time or near real-time responses. This growing demand is exposing limitation on our traditional cloud computing models, leading to emergence of fog computing. Okay. Think of it like basically if every action in your body required instruction from your brain, you wouldn't survive. Right? Some decisions must happen instantly and locally. That's exactly the gap fog computing fills in digital systems. Okay, I'll take a couple of examples, right? Take an example of self-driving car. If an obstacle appears, the decision to brake cannot wait for a cloud response. Or in a manufacturing client, for example, if a machine overheats, stopping it locally is far more important than sending data for logging into the cloud or central location. All of these systems requires low latency, high reliability, and local intelligence. Now, from an academic perspective, this is a classical distributed system problem. Where should computation happen basically to optimize your latency, reliability, and cost? Before we go any further, some other real world scenarios, as you can see, right? Fog computing may sound like a new concept, but in reality, it is in the use for decades. We all must have worked or seen these in action in real world across our journey. Consider a modern elevator system, for example. When you enter a lift or an elevator, the decision to stop an elevator immediately when a door is blocked does not go to a central data center or a server, right? It happens locally on that elevator. However, for your long-term optimization like usage patterns, maintenance schedules, this is handled centrally. Okay, and that middle decision layer is conceptually very similar to fog computing. Another everyday example is our mobile networks. When we make a call or stream a video, not every decision goes to central core network. Many decisions are handled at regional network nodes to reduce latency and improve reliability. Now, fog computing applies same thinking to digital systems, which are built on your cloud and IoT devices. Okay. Now let's take a more technology centric example, if I may say. Think about online fraud detection applications. If every transaction had to be analyzed centrally before approval, the system would be extremely slow. Right? Instead, lightweight checks happen close to the transaction, while deeper analysis happens centrally. And fog computing generalizes this idea for large-scale real-time systems. Okay, if I may summarize, right, the key takeaway basically for you is fog computing is not about inventing a new layer for its own sake. It's more about recognizing that some decision must be made close to where event occurs, while other benefit from your centralization. Okay, this perspective is important because it helps us avoid thinking of fog computing as a product or a trend. It's not a product or a tool which you can just add in and plug it in your environment and it happens. It's more like an architectural response to address how real systems behave in the real world. Okay. Another key point which a lot of people usually get confused or ask question is that fog computing exists not because cloud failed or anything else, but because cloud alone is not enough for modern real-time distributed systems. And we'll see in upcoming sections where we'll see from live examples, right? Now, before we talk specifically about fog computing, it is important to go back and see how the computer paradigms have basically evolved over time. Most of you must have already know about these, right? These paradigms has not changed randomly. It is basically an evolving phase where always it's a response to scale, user needs, and technology constraints. Okay. In the beginning, in the earlier days, when I started my career, right, we started with mainframe computing, where everything was centralized. Users were basically your dumb terminals, if you know about it, and intelligence was only living in one central place. Then we moved to client server computing model, where the processing was more shifted towards users, but server were still playing a major role in your environment. Post that, we moved to the cloud computing, which again re-centralized the whole computation platform, but at a very large or a massive scale with key features like your elasticity, global access, and stuff like that. Okay. With IoT coming in, with cyber physical systems and all the real-time applications, we are now seeing another shift towards distributed and near edge computing. Okay. Now, this evolution is not just academic. Industry systems which we are having today basically are always operating in an environment where, as we discussed in initial slide, data is getting continuously. Decisions has to be made in instantly, like in milliseconds, and connectivity is completely unreliable. That's why there is a force to move computation more closer toward your source of data. Okay. Now, from an academic standpoint, this is more like a shift from your purely centralized distributed systems to more of a hierarchical or a geo-distributed system. And then it's not part of natural evolution. It's more of a disruption. It's more like an extension to cloud that we will see. Okay. Now, fog computing also didn't appear suddenly. It has emerged because neither your full centralization nor decentralization works on its own, right? Okay, now let's move on to the next topic basically, right? So now we have seen how computer paradigms have evolved. We need to examine where cloud only approach starts to break down. Okay, you just referred into the edge computing in the previous section in detail. You must have also seen cloud computing, which has been incredibly successful. I myself have spent years on the cloud computing, where we have features like scalability, elasticity, and a lot of cost benefits which organizations are achieving through that, right? But when we are developing and architecting solutions on cloud, one of the couple of key assumptions are that centralized processing, and we always have a reliable connectivity. But in the current modern systems, there are some challenges which comes into picture. And these are the ones which you can see, right? The first one and the most critical is your latency. When data has to travel from a device to a distance data center and back, the delay is unavoidable. For applications like autonomous systems, industrial control, medical monitoring, even a small delay can have some serious consequences, right? And then we have examples, some breaches recently happening wherein, let's say in a medical environment, a delay on your application can actually have serious consequences for your patients, right? The second issue is bandwidth. Streaming raw data, especially your videos, all of your sensor feeds, your telemetry coming for devices to the cloud basically becomes more expensive and inefficient. The third one is reliability and connectivity, wherein let's take an example like cloud computing assumes stable high speed internet connectivity. But in real environments, be it factory or a remote location or recent example of moving vehicles, right? Connected cars, experiences intermittent or unreliable connections. When these connectivity fails, cloud dependent system degrade or stop functioning. And then that becomes a real life challenge for organizations. Finally, there is security and privacy concerns. So sending all the data to cloud increase your attack surface and raises serious concerns about your data sovereignty, compliance, and exposure of sensitive informations. It's more like outsourcing every decision to remote office. It works well for planning and reporting, but it's not so good for emergencies. Okay. Now, cloud basically optimizes for scale, but not always for timelines and locality. The key point out here that I would like to make is that these limitation does not mean that cloud is bad or not suitable for organization. It simply means that cloud needs some supporting layers. Okay, and that is exactly where fog computing enters into the picture. Now, before we jump on, let's do another quick poll. This one is very important on what comes next, basically. So the question is, where should real-time decisions ideally occur? You have 4 options. Please don't overthink it. Answer based on your current understanding or intuition. We'll give 15-20 seconds for responses and then we'll have a quick review. So if you can put in the chat on the responses, that's good. Okay, I don't see the responses coming in. I hope you have access for this, or if possible, you can come unmute and give your responses as well. Here, Sridevi says A, which is cloud. Okay, I think let's move ahead. The poll basically was just to understand on your inputs, but there is no single correct location for all these decisions, right? It totally depends on how you want to layer the architecture or how you want to basically build the modern architectures, okay? Because we will see how modern architectures are basically layered architecture. Okay, so before we go into any formal definitions, let's start with explaining fog computing in the simple analogies that we have. Okay, I just touched upon in the previous slide itself, right? Imagine in real life how you make decisions, or in real life how decisions are made. If we talk about a large organization, for an example, strategic decisions, example, long-term planning, are made at the headquarters. Okay, your day-to-day operational decisions must be made at regional offices. Okay, and then immediate on-the-ground decisions are always made by the local teams which are running there. In this similar analogy, the headquarters represents your cloud, local teams more are like your edge devices, and the regional offices is something which represents the fog layer. Okay, you basically wouldn't run an organization where every local issue has to wait for approval from headquarters, and you also don't want to give local team a limited authority, and that's why you have this middle decision layer. So fog computing plays exactly this role in modern digital systems, balancing speed, intelligence, and coordination. Okay. With that intuitive picture in mind, let's now look at how cloud, edge, and fog basically are different from each other. I think this comparison will give you a brief view on how it needs to move from further ahead. So this slide gives you a high-level comparison about cloud, edge, and fog. So rather than thinking them as competitors, right, you need to understand that these are more of a collaborators in a layered architecture. When the cloud provides you massive compute power, global visibility, and long-term analytics, it is ideal for training models doing historical analysis, or doing some centralized coordination. On the extreme other end, edge devices, which are closest to the data source, they enable ultra-fast reactions but are limited in compute and storage. So for example, right, you have your smartwatches on your hand. They can be more reactive to certain events that may occur, but they have limited compute and storage. You send that data to cloud. Cloud provides you a good compute power, long-term analytics, and all those stuff, but it is slow, right? And in those scenarios, fog sits somewhere in between, where it is closer to cloud, closer than cloud, but more powerful than the edge. It aggregates, filters, makes real-time decisions here, right? Each of these layers is optimized for a different class of problems. Okay, we can go into a bit deeper into the next slide, which is there. I'll not cover much detail out here because we have limited time out here. I'll share these slides with you, but would like to talk about a couple of pointers from this, right? So for example, latency. If you talk about latency, this is lowest at edge, slightly higher at the fog, but it is maximum in your cloud. Okay. Another important aspect is your bandwidth usage. Fog reduces bandwidth by filtering data before sending it to cloud. So you are consuming less bandwidth on your network. Right? Similarly, scalability is another key thing which comes out of this comparison. Whereas cloud can scale globally, fog scales usually regionally, and edge is more scalable at locally, or very limited scalable capability in the edge devices. Security and control. This is one of the key factor and decision while addressing these selections. Fog enable you localized security enforcement and compliances. Okay. From a system perspective, this is more like a hierarchical distributed model and not a flat or not a centralized kind of a model. Okay. Now that we have compared all these three layers, we are ready to formally define what fog computing really is. And I'll basically let me read through the formal definition, because in this setting, I think it's important that we anchor ourselves with the standard based thinking. So this one is actually coming from NIST and IEEE, and what it says is fog computing is a distributed computing paradigm that extends cloud computing services to the edge of the network, enabling computation, storage, and networking closer to data sources to support latency sensitive, real time, and context aware applications. Okay. Now, don't worry if this is too dense. That's normal with all our formal definitions which comes out. Okay. We will break it down in simple terms. So distributed computing paradigm. This tells us that fog computing is not a single technology or product. It is more like an architectural approach that we have covered earlier as well. Okay. Extends cloud services closer to computing services. Fog does not replace cloud. It ideally extends it. So you are basically extending computing power to your edge devices, near to your edge devices, and thus reducing load on the cloud platforms. Closer to data sources, same thing, right? This is one of the key motivation. You are reducing delays, you are reducing unnecessary data movements, and thus providing low latency environments. The last, which brings to the last one, which is latency sensitive and real-time applications. This basically tells us exactly why fog exists in real world. Okay. In simple terms, if I put it into very layman language, fog computing simply means that don't send everything to cloud, process what matters and where it matters. Fog computing doesn't replace cloud or edge. It basically connects them intelligently. And we will see how the trends are coming in with AI coming into picture on fog computing and edge devices, where a lot of decision making happens automatically between these devices. Okay, fog computing is more about your placement of right computation at right location and at the right time. Okay. All right, now that we have a formal definition of fog computing, let's take a look at the key characteristics of fog computing. By now, I think you must have already got a picture of what key characteristics fog computing comes with. These characteristics help us recognize whether a system truly classifies or qualifies for a fog computing or not, right? Uh, First is low latency, like fog computing is designed for latency sensitive workload. That's the first requirement that you have. So processing happens close enough to data source to enable near real-time responses. If not real-time, it's near real-time responses which it caters. Okay. Second is location awareness. So fog nodes are aware of their physical or network location. This is critical for applications like smart traffic system, industrial automation, where the device and the compute environment must be aware about their location so that the right decision can be made at right time. Okay. Fog computing also follows a hierarchical model. So that's another additional thing that you should be aware about, that edge, fog and cloud all work together in a hierarchical model, which improves the scalability and fault tolerance for your environment. Right? Now, fog architectures are also designed to support moving devices like vehicles, your drones, your wearables, all these things wherein the device itself is on the move. Fog architecture are designed to support those devices. Okay. Another key important characteristic is sensitive data, which cannot be processed locally, basically, and thus you are reducing the exposure and supporting a lot of compliance related activities. In addition to all these listed characteristics, there are few other traits which basically you should be aware about when you're talking about fog computing. One, the fog nodes are not are basically geographically distributed. Okay, it's not centralized like your cloud data centers. These are distributed across different regions, locations based on your environment and your factory setup, etc. Next is fog systems also understand the context. So it's not only about data that is getting generated. It is not only about data readability and further processing. These systems understand the context as well and then takes a call out of it. Fog also enables analytics at the moment the data is generated, not after the fact. Okay, so taken all of these together, these characteristics make fog computing ideal for your system that are distributed, time sensitive, and context driven. Okay. Now that we know what fog computing actually is, it is also important to understand what it is not. Okay, because a lot of time we have seen that fog computing is often misunderstood, and that's why this slide is very important for us. Let's clearly state what fog computing is not. So it's not a replacement of cloud. Fog computing does not replace cloud computing. Cloud remains essential for your centralized analytics, your global coordination, large scale model trainings, or long-term storage capabilities. Fog complements the cloud. It does not compete with it. Right? Another misconception is that fog computing should be used everywhere. And that is also not true. Fog is valuable only where, as we have seen earlier, where latency, locality, and bandwidth constraints are there. So you need to align there. Fog computing is also not same as edge computing. Okay. Edge devices typically perform very limited device specific processing. Fog, on other hand, serve multiple edge devices. So you can have hundreds of edge devices which can be handled by, let's say, 20 or 10 fog nodes in your middle layer. Okay. One related misconception that I often hear in fog computing is that it's just a gateway device. So gateways can act as fog nodes, but fog computing itself is an architectural concept and not a single device. Right? Now, finally, fog computing is also not tied to any single vendor or platform. It is more of an architectural paradigm defined by certain standards and principles, not by any products. This is especially important in the academic and research context if we are talking about that. Okay. Now, one key thing that as an architect or as an industrialist you would be understanding is that fog computing is more of a design choice and it's not a default. Okay. Now let's again pause for one more quick check-in, Paul. By now we have discussed about what evolution of cloud computing, cloud limitations, comparison with edge, and a formal definition of fog computing. So based on whatever we have gone through so far, how familiar were you with fog computing as a concept? If you can quickly put in your responses and then we move from there. We had few responses earlier, so which is also fine. Okay, so Jiti says expert. That's great. All right. Hardik says basic. Okay. This is good. So regardless of wherever you have started, right? By end of this session, you should be able to clearly explain like what fog computing is, where it fits, and why it matters. Okay. With that, we will move to the next one, which is basically the architecture. And this is one of the key and the core thing that we should be focusing right now. And very important section. Now, since we have understand both concept and audience comfort level, let's move into how fog computing is actually structured and used in practice. Okay. Now we are going to shift from concept to structure. So fog computing is best understood through its architecture, and if you refer most of the models, structures that are available, basically define it as a 3-layer system, which you see in the diagram right now, right? In 2014, Cisco came up with this terminology of fog computing when they were actually working on addressing these challenges, which we discussed about cloud and edge devices. And a lot of Cisco products and the devices that were there at edge, which was handling such computation, they come up with this terminology of fog computing. And this is a 3-layer system, as you can see on your screens. Now, at the bottom, we have the edge layer, where all of your data is getting generated. In the middle layer, the fog layer, where near real-time decision happens, which we have been discussing, right? And at the top, the cloud layer, where large-scale analytics and all the coordination occurs. Okay. Now, certain things which are very important to understand in the architecture itself, that these layers are not silos. They basically collaborate with one and each other. The whole idea of having the fog computing architecture is that the intelligence of the system comes from how work is distributed across these layers. So that decision making is something which makes fog computing architecture more relevant into today's modern system, right? If we talk about data flows, right? Data typically flow from your edge devices up to cloud. So it's typically flowing upwards, if you may say, in this diagram, but decisions don't always flow back down from cloud. So that's the key difference you should understand. Many decisions are resolved at the fog or the edge layer itself. Okay. Before we go deeper into individual layers, let me add one more important architectural concept that will help you understand and make sense of fog computing, and the idea which we were discussing about where decisions and control actually live. Okay. In cloud environment, you must have seen, right, that we have a lot of applications have what we call as data plane and control plane. So data plane takes care of whole of your data related aspects, the processing of data, movement of data, and all those stuff. While the control plane is where the orchestration happens, the control comes in, all security guardrails, policies, etc. comes into picture. Okay. The data plane is about fast movement and processing of data, sensor readings, your telemetry devices, your video frames, etc. Okay, and control plane is more about orchestration, deciding what runs where, which is a very critical decision, applying your policies, managing behavior, and so on. In fog computing, this separations becomes extremely important for us. The cloud typically hosts a significant part of control logic, like global policies, your AI model updates, your optimization strategies for your whole infrastructure. The fog layer, however, executes the data plane decisions locally. So basically, it's very close enough to meet real-time constraints. And this is why fog computing is not just about where data flows, it's also about where control decisions are allowed to happen. Okay, before moving ahead, I'll take a pause if any questions so far, and before we jump into details about each layer and architecture. If any questions, feel free to unmute and ask in between, or put it on chat and I'll read and respond in between. Okay, if no questions, I think we can move on. So in this architecture, another useful way to think about is basically from a latency budget perspective. You must have seen, or you might be aware that different application can tolerate different delays. So let's take an example. Again, I'm going back to the connected car example or connected vehicle examples. Emergency braking in a vehicle needs decision which should be very minimalistic, let's say under like 10 milliseconds or so, right? That when the brake should be applied, the vehicle should be able to call that out immediately within 10 milliseconds. Otherwise, it's lethal for the passengers. Okay. Similarly, industrial safety shutdowns may allow 10 of milliseconds, right? Because it can have some decision making power at the end. You can make some calculations and then go about the safety shutdowns in an industrial environment. Similarly, in a business analytics environment, you can actually tolerate seconds or even minutes. If your business analysis is delayed by, let's say, 5 minutes or so, it's not business critical. It's not something which will have lethal impact on any human lives, etc. Right? And that's where this latency budget comes in to calculate which layer should be organized in your architecture to perform certain activities. Fog computing exists to basically satisfy your middle latency band where your cloud environment is too slow. Okay, and your edge alone is not capable enough to handle that. All right, with that, maybe we should get into the individual layers then. Okay, now we are talking here about the very first layer, which is your edge layer, and this is where everything begins. Okay, This is where data is created. It's basically contains of all your sensors, your cameras, machines, medical devices, vehicles, smart meters, and then whatnot. Okay. Edge devices interact directly with your physical world, as you see. Okay. They capture raw data and may perform very basic processing, such as filtering noise or triggering simple actions. Okay. So for example, if you have a health band that you are wearing as your wearable device, right? You can set certain alarms. You might have seen right nowadays people are setting up alarm for their water consumption in throughout the day. When you have completed, let's say, certain exercise or activities in the day, your number of steps, and it just gives you some alarms, etc. So these kind of activities are performed at the edge location to be very easy, right? Now, however, these edge devices are also constrained. They will have usually very limited compute power. The storage is always a challenge. All these small devices will have limited storage capabilities. And similarly, these security capabilities are also limited with these devices. Right. So when you talk about these edge devices, you don't have much control of how the access will be managed, how your data which is being processed locally is being controlled. You don't have access and visibility onto these components as well. This is why the edge computing alone doesn't work enough for a complex system. So your edge is basically fast, but it's not too powerful to handle all these kind of scenarios. Okay. From a systems perspective, if I may say, right, the edge layer prioritize your responsiveness over complexity. Let's pause briefly and then go a little bit deeper into what we really mean by the edge layer, because edge is also often misunderstood. And in the previous section, you have gone in details on edge computing itself. So not all edge devices are same. That's one thing, right? Some are extremely constrained. So in a factory setup or in an OT environment, if I may say, there are certain sensors which would be very limited and a constrained environment, like a temperature or a pressure sensor, for example, right? It just captures certain parameters and give you that value out from as a data point. Others are like camera or industrial controllers, which are far more capable, but still limited compared to your server devices. Okay. The key point is that edge devices are always specialized. Whether it's one particular sensor or one particular device, they would have one or maximum of two activities to be performed at your edge location and interact with your physical world. They are optimized for interacting with physical world and not running your complex analytics or coordinating with many devices. So taking example of the factory again, right? You have your temperature sensor, you have your pressure sensors. There are devices controls sending feeds from your cameras. All of these individually works for one particular purpose, but they cannot interact together. They cannot send data across devices or make references out of it. Right? In a well-designed fog architecture, edge devices will typically do certain specific things, right? One, they will capture raw data for you. They will basically perform basic filtering or certain threshold checks, as same example of temperature sensors, right? You can have that sensor record the data, put a threshold of, let's say, 75 degrees Celsius, and it will basically trigger that and filter the data out. And that immediately triggers a safety action if needed. So these are certain things which edge layer will perform for you. What they usually would not do is any kind of heavy analytics, any kind of cross device correlation, or any kind of long-term learning. Okay, let's take an example for this. A camera at an edge location, it can detect the motion. from the camera feed. But determining whether that motion is actually an incident happening in the location often requires correlation across multiple cameras. Okay, so you may have 20 cameras put in. One feed coming from one camera doesn't define an incident. But if multiple camera feeds are correlated together and it comes out that there is some event happening at the location, that's what matters for me as an architect or a industrialist out there, and which is where fog comes in. Okay, so with that, we'll move to fog layer itself, which is more like the central layer, right? So if all these edge devices, which we just discussed, are fast but limited, the very next question, obvious question, is where do we place more intelligent processing without going all the way to the cloud? And that's the limitation of cloud that we have discussed earlier, that we cannot send everything directly to cloud. For edge layer has its own limitations, and that's where the fog layer is heart of the fog computing. It sits between your edge and cloud and exists specifically to handle near real-time intelligence. Now, fog nodes are typically gateways, local servers, your telecom edge nodes. It can be your on-prem infrastructure also. They serve multiple edge devices within a local domain. Right? I was explaining this earlier, right? Your edge devices can be in thousands, and then certain number of fog nodes will cater multiple edge devices within that particular location or a domain. Now, what basically is happening at the fog layer is we are performing data aggregation, we are performing data filtering, then certain real-time analytics being done at the fog layer itself. Okay, all kind of policy enforcement, whether it's security related, your device related policies, that happens at fog layer as well. And then very important, security monitoring also happens at the fog layer. Okay, so you are basically going towards and monitoring this security as well. Fog combines your proximity with the capabilities. Okay, it is close enough to be fast and powerful enough to be intelligent as well. Now, if we compare with the initial example which I gave at the beginning of the session, right? If your edge devices are like reflexes and cloud is your brain, the fog layer is your spinal cord. So which is capable of fast and coordinated responses without consulting your brain every time. Okay. Now, if we talk about academically, how does it get related to concepts, right? Fog node basically act as a intermediate control and computation points in a hierarchical distributed system. And this is the whole point in the architecture where fog computing truly differentiates itself. So let's take some time, get into details about fog as well. So fog layer acts as your local brain of the system. Okay, we discussed in the edge devices that they don't have enough compute, storage, and context understanding. Unlike your edge devices, fog nodes have enough compute, storage, and context to understand that what is happening across multiple data sources. So that correlation capabilities that we discussed, all those things basically happens at your fog layer. One capability, the correlation part which I'm talking about. So let's say a single sensor spike is irrelevant for us. But when these individual correlated signals across multiple sensors are combined and correlated, it often indicates a real event for you. And fog nodes are specifically designed to perform these kind of near real-time correlations. Another important aspect is about placement. Right? So fog nodes are typically deployed where it makes architectural sense. For example, on factory floors. In hospital, you have your on-prem infrastructure. We will discuss about healthcare industry also. So you have on-prem servers which are taking care of feeds coming from multiple devices. at telecom base stations, right? In a transportation system use case, you have roadside units installed to cater to this. In many cases, as I was saying earlier, fog infrastructure already exists. It has been there for decades. It's just may not be called as fog computing earlier. From a processing perspective, fog nodes often maintain very short-lived state, right? So on one end, you have edge devices, which are mostly stateless. Cloud system maintain long-term states, while fog sits in between, right? So edge devices, you collect the data, you have no state pending. Next time the data comes in, it's all afresh. Fog sits in between and it just remembers enough to make intelligent local decisions coming out of it. Okay. Security is another critical function for the fog layer. As I was saying earlier, fog nodes basically can authenticate your devices locally. So you have an authentication mechanism. You can put in some identity related controls on there. You have capability to enforce security policies. Okay. Although these policies come from top down from cloud, where you define your global policies, the fog devices are something which enforce these security policies on ground. Okay. It also helps you detect anomalies before the data ever reaches the cloud environment. This significantly reduces both risk and any kind of unnecessary exposures. Okay. Now, there is one more key aspect which has just cropped up in recent times, and this is where AI is also becoming operational. So in modern systems, we are seeing that AI models are now being trained centrally on cloud. Okay. AI inferences runs at the fog and then actual actions are executed at the edge. Okay. I think there was a question in the previous section at the end when I joined in about how AI is being used in edge and with agentic AI coming in, how this is being leveraged. So this is how it basically ties back to the whole story. Your models are getting trained on the cloud, your inferences are run at the fog, and then your agents are taking action which are executed at the edge location. Okay, so if we compare it in that sense, fog is where AI is actually meeting the reality of the world. All right. Any questions? I know it's a bit deep and it's very important as well. So any questions on the fog layer? You can have it at the end or you can ask me right now as well while we move to the next layer. Now we have seen the near real-time decision happens and how the role of cloud in this architecture is. Okay, the cloud still remains a critical part of your overall architecture or your fog computing architecture. It doesn't reduce the importance of cloud. It makes it more effective. Okay, cloud is still ideal for your large scale analytics, your long-term data storages, your training of AI models, ML models, and all the global scale and the coordination across regions. The key difference being cloud no longer processes everything. It processes what truly benefits from centralization. Okay, from a security governance perspective, fog reduces unnecessary data movement while cloud enforces global policy. Okay, in fog computing, cloud becomes more of a strategic choice, not a reactive choice. It is important to emphasize that fog does not reduce the importance of cloud. It actually makes it more effective. Okay, the cloud becomes your system's memory. It is still storing your historical data, identifying long-term trends, performing large-scale optimizations. There is also a feedback loop, which we say right at play. So cloud is refining your models and policies based on the aggregated data that is pushed through fog nodes. These updates are then pushed back down to your fog nodes, and then fog nodes adapts their local behavior accordingly. So it's a cyclic process, as I was saying in the beginning, right, it's all about collaboration between these three layers and how intelligently decisions are taken in different layers depending on the scenario. And this creates a closed loop intelligent system rather than a one-way data pipeline in a typical environment. Okay. Now that we have understood the full architecture, all three layers in detail, we also are in a position where we can see the technologies that enable your fog computing. Okay. The important thing to understand is fog computing, as I have been saying, did not appear because of one breakthrough. It is already there. And it is basically possible because of multiple mature technologies that has come together over time. Okay, few of those which are listed here, you all would be across these as well. First is virtualization, right? And more importantly, today, containers. Correct. Now, containers are particularly important because fog nodes do not have the scale which a cloud can provide. Virtualization and containers provides you because basically it provides you your application to start, stop, and move quickly. If you know about containers, you know that this is what the beauty of container is, that it gives you flexibility of spinning up environments fast in an agile manner and shut down also when not required, right? Which is critical in geographically distributed environments. The microservices architecture is another key enabler for fog computing. Fog workloads are naturally modular. So you must have seen, right? One service might perform filtering, another might perform inference, another one is handling just the alerts. And all these modularity comes with the microservices kind of architecture, which we perform. Orchestration in fog environment is more complex than in cloud. And unlike your cloud environment or data centers, these nodes are distributed. So sometimes intermittently connected also. And that's where it becomes more important to have a lightweight orchestration enablement, and tools for that are easily available. And then also the IoT communication protocols that we have, right? That's one of the key important because your fog layer is communicating very closely with your edge devices, and all these communication protocols comes into play when we are talking on that end. And another thing which I was talking about recently was about AI at fog, which is growing rapidly. Running inferences locally basically reduce that latency and protects your sensitive data and allows system to keep functioning even when cloud connectivity is basically degraded. Okay, with these technologies in place, we'll just step back for a while and look into the next step, which is basically why fog computing matters. By now, you would have enough details about that thing, right? It's simple. Fog computing matters because it directly addresses the gap that we discussed in the beginning on the cloud-only systems. Okay, by processing your data closer to its source, fog computing dramatically reduces your response time, which is critical for real-time systems and thus reducing latency. Fog filters your and aggregates data locally, so only what is meaningful is sent to cloud, and thus you are reducing your network load and cost. These systems continue operating even when your cloud connectivity is limited and or unavailable, and thus you have improved reliability. The sensitive data is remaining local. You are having policy compliance as well. That's where the compliance, privacy, and risk reduction is also happening. Okay, fog computing matters because it enables systems that are fast, resilient, and intelligent by design. Okay, let's pause again and we'll again have a quick poll. It's not moving. Okay, we'll again have a quick slide on the poll on to see how this value translates across various industry. So based on what we have discussed so far, which sector do you think gains maximum value from fog computing? Is it smart cities, healthcare, manufacturing, or all of the above? We'll give 15 seconds if you can put in your responses. Okay, I think it is not coming up right now, but very simply, if I put it in a simple way, fog computing, yes, Hardik, should be you correct, right? Fog computing is valuable wherever you need to have fast decision making, your data is distributed, and wherever context matters. Okay. Now let's jump into some of the cross-industry relevance that we have just seen the responses, and oh, PPT is not available. Is it so?
It's visible, sir.
Okay, okay. I think someone just pasted that it is visible. It is not visible. Okay, so let's take an example now. So we will move on to the next section, which is more about use cases and how it is being used today in real world. Okay, I am taking the first example of smart cities. I hope most of you know, right? Smart cities are one of the earliest and most visible adopter of fog-like architectures, even if we don't always use the term fog computing explicitly. So let's take traffic management as an example. In large cities, adaptive traffic light process video feeds locally at intersection or regional control centers. They don't stream every video frame to central cloud. Instead, they detect the congestion, accidents, or violations locally and respond immediately. Okay. Studies in intelligent transportation system consistently show that local processing of these devices reduces your response time from seconds to milliseconds, which directly impacts the congestion and the safety in your cities. Okay. If I talk about your public safety systems, okay, video analytics such as subject detection or crowd monitoring are increasingly performed at local nodes. So that's one of the key use cases in smart cities as well. Only alerts are summarized. Metadata is sent to central system. Okay, and why fog fit here? Because videos are of high bandwidth. We need real-time responses here, and obviously the privacy and the sensitivity part of it from a security perspective. Academically, this also maps to your research in real-time video analytics, your distributed controls, and geo-distributed systems. Now, smart cities basically don't become smart by collecting more data. They will become smart by deciding faster and closer to problem. And that's where the fog computing is widely used nowadays in the smart city deployments. Okay, fog nodes are not actually placed at intersection or regional points. It also allows to respond locally while still contributing to data to citywide optimization. All right. Let's move to the next. The next one industry example that I would like to call out is around your healthcare industry. I touched upon it in the earlier section also, but healthcare is where fog computing moves from being just a performance optimization to more of a critical architecture requirement. Okay, let's again take an example of your wearable device that monitor your heart rate, oxygen level, or glucose level. These devices generate continuous streams of data, and in real-time environment or in real deployments, abnormal patterns are basically detected locally in either in your hospital environment or on some local gateways, and then alerts are generated and sent immediately. Healthcare systems globally are moving towards edge or near edge analytics specifically because of this cloud latency, which is unexpectable in an emergency situation. Okay. Now, within hospitals, fog nodes are often deployed as on-prem servers that integrate data from multiple devices. So you must have seen in the hospital, like there are multiple monitoring devices in patient's room, which are collecting data. Locally, it is also showing you that values, but it is being collected on some on-prem server or a device, which act as a fog node for you. And this basically ensures that an immediate alert is generated, reducing the network load on with the cloud and better compliance with the data protection regulation. And then that brings me to very key important point on healthcare industry, because regulations like HIPAA and similar data protection frameworks in healthcare industry strongly discourage any kind of unnecessary data movement, which fog architectures naturally minimizes. Okay, fog computing is enabling the real-time care without exporting your raw patient data. So you are meeting that security. The next update, just one more thing, right? From a healthcare perspective, another key challenge is also the false positives. So individual reading can fluctuate naturally, but as we discussed about the correlation capability of fog layer, fog nodes help by correlating trends over time before raising any kind of alert. So that's another view where healthcare industries are deploying these fog nodes for review. Okay. Now, the next up is manufacturing environment also, right? Industry 4.0 or manufacturing environments. These are the early adopters of fog computing principles, much way before the term become popular itself. Okay. In all the modern factories, many of machines are instrumented with vibration, temperature, pressure, and acoustic and whatnot, different kind of sensors. Fog nodes on factory floor basically analyze all of this data in real time to detect any kind of anomaly. Industry studies basically show that predictive maintenance can reduce unplanned downtime by 30 to 50%. Okay. We cannot afford production being stopped just because the connectivity to cloud is lost. And that's where fog-enabled systems continue operating autonomously even during network disruptions. Okay. In my previous experience, one of my previous experiences, I was working for a diamond mine in the North America region, and we had all the cloud and virtualization set up, but on the field for the mine, we had certain dedicated on-prem servers, which was acting like a fog node as we are seeing now right now, because there were a lot of sensor controls and data which were going through those fog nodes first, and all the active actions were taken from that fog node rather than sending it to the central data centers across the globe. Right. So that's the benefit that is coming out of fog computing. Right. Now, fog computing turns your factory from reactive systems into anticipatory systems. So in this environment, it's more about anticipating the changes and having that cost benefit coming out of it. Okay. The last one for us today is basically the transportation and energy sector. I've been giving examples on transportation, connected vehicles throughout the course itself, right? Connected vehicles generate data related to speed, your braking, your road conditions, etc. In an environment, roadside fog nodes will basically process this data locally to support any kind of collision warnings, traffic coordination, and stuff like that. Now, safety critical vehicular system typically requires responses under 10 milliseconds. We saw that in the latency budget section also, far below what cloud will provide you. Okay, and in case of smart grids, for example, fog nodes monitor local substations and your distribution points. When a fault occurs, local isolation happens immediately to prevent cascading failures. Okay, so grid operators globally use localized automation to improve resilience and reduce outage duration. Okay, now across transportation and energy, fog computing enables your that local autonomy with global coordination. Okay, in transportation energy, it is supporting your continue to operate safely when disconnected from central control. Okay, so we have seen these 4 use cases, and across use cases we have seen, right, how it enables global coordination, how it provides global autonomy, how it helps you save the cost, and how it basically help you generate security and privacy. Okay. So we have looked into so far we have looked into what fog computing is, okay, how it's structured and where it's used successfully. Now let's talk about other side of the story, the challenges and open research problem right now. Like any other architectural concept or technology, fog computing also has its own challenges. And before we move into formal research challenges, one thing to note is that fog computing is not a solved problem yet. The key strength for fog computing, which is the distribution, is also its biggest complexity. This is precisely what basically make it such a rich area for any kind of academic research and areas to explore further. Fog environments are highly distributed and heterogeneous. So deciding where to run a workload, when to move it, and how to balance load is a trivial problem, non-trivial problem for us right now. Some of the areas that we need to explore is more about defining certain scheduling algorithm, for example, handling the dynamic placement of your resources in fog environment, and making it latency aware orchestration. So in a fog environment, if these problems are solved, I think it will make more sense for wide adoption, right? Uh, Fog nodes are again geographically distributed. That's why it's possible that it's deployed in less controlled environments. Again, I go back to my experience, which I was talking about in the diamond mines. The servers there were still running on, let's say, old NT Windows NT environment due to certain limitations on their applications, right? But if I view from a security lens, it still is not a feasible and a good approach that they were taking. But this raises concerns about trust authentication and secure coordination. So what we need to do more research right now on fog computing is how do we build a zero trust model for fog environment? Okay, how do we secure boot and do attestation for your fog devices at edge locations or non-edge locations? How do we handle the insider threat detection in your fog devices? So these are all areas which comes into the security and trust bucket for fog challenges. Okay, processing data locally help privacy, but it also introduces a lot of governance complexity especially when we are talking about jurisdictions, right? So we need to understand more about how do we make sure that privacy preserving analytics is being done? How do we do more of data residency models, right? The policy enforcement, if I may say, right? The other aspect that we are seeing a lot nowadays is like about standardization and interoperability. So this is one of the things that fog computing lacks as like a single dominant standard today in the market. Okay, interoperability across platforms and vendors still remain an open challenge for us, and the protocols are defined, but there are still a lot of other vendors and platforms coming up, so that interoperability is still a challenge for the real life scenarios. Okay, these challenges make fog computing extremely rich area for academic research, especially in distributed systems, security, networking, and the new topics like AI. I've been working on defining certain topics around AI at edge and AI at fog on what we were discussing earlier, how inferences are now moving more towards fog and the edge layer. So that's one of the key areas to focus in terms of more research around this. Okay. Looking ahead, let's explore where fog computing is moving next in our goal. Okay, so these are certain future trends, if I may say, right, on the fog computing part. So it's not a static concept. It's basically evolving alongside all other major technology trends that are happening today, right? We are seeing a clear separation. AI models are trained at the cloud, and AI inference is happening at fog or edge. This enables faster decision, reduced data movement. So we've talked about this, which is moving forward. High-speed, low-latency networks makes fog architectural even more powerful, right? Especially for mobile and your real-time systems. So the 5G, 6G integration is something which is happening fast, and we will see a lot of trends moving toward that as well. Instead of sending data to central location, models are trained across distributed fog nodes. Okay, and that takes care of that federated learning portion. Okay, which is again very important from a perspective that a key important research driven trend is this federated learning, right? Fog nodes plays a critical role here. They coordinate learning across multiple edge devices while still preserving your privacy. This is particularly relevant in domains like healthcare and finance specifically, where raw data movement is heavily restricted across the board. Okay, digital twins and cyber physical systems is very critical. Fog computing is also becoming a key enabler for your digital twins, right? So if we see digital twins require near real-time synchronization between your physical systems and your digital representations of those systems. Now, cloud alone in these scenarios is often slow. And that's where fog provides that responsiveness that is required to keep digital models aligned with the reality. Okay, looking ahead, systems are expected to operate with greater autonomy. Connectivity failure will lead to system failures, and then these connectivities, automated resiliency is something which is very important as a future scope also. Now, if I summarize this very importantly, right? The future of computing is neither centralized nor decentralized. It is intelligently distributed, and fog computing will be a foundational part for that future. Okay. With that perspective, let's summarize what we have covered today. It's not moving. Okay, and before we close, just stepping back and having a very clear view on why fog computing matters both academically and industrially, right? From an academic perspective, fog computing is bringing your multiple foundational areas, right? Be it distributed systems, your computer networks, your cyber physical system, security, privacy. It's provide you rich material for all your student project research PhD works, and many of these challenges which we discussed, scheduling, security, orchestrations, are all open research problems. Okay, from an industry perspective, fog computing is not theoretical, it is already being applied. Is there a question? No. All right. Okay. From an industry perspective, as we were discussing, right, industry may not always call it fog computing. We have seen that we have been using fog computing since decades, but the architectural pattern is still widely used and we may not call it fog computing. One of the critical takeaways would be that fog computing is one of those rare areas where academic research directly informs your industrial practices, and then the industrial challenges feedback into the research in this area. Okay, I think with that, let's quickly. Hello, is there a question? We're just opening up questions.
Dear participants, if you have any questions, you can ask sir right now.
Sir, now some questions came up during the session, but got answered in the due course. But finally, you said that there are certain industrial challenges that can lead to academic research. Can you explore a little more on that?
Sure, let me just go back to the same slide also for your reference. Just a second, I think it got disconnected. Yeah, so I think if I just summarize, right, what I was talking about, those challenges.
Yes, sorry, yes.
Yep. Hello?
Sir, please proceed, yes.
Okay, okay. Yeah, so I was just mentioning, and let me just share my screen also, and I just realized I think the video also paused. I'm not sure for how long, but I think the video was also paused for me. Yeah, so these are the industrial and academic relevance which we were discussing earlier, right? Now, in terms of research topics or the challenges that we were discussing, certain things are there, right? Because this is more like we were talking about the AI challenges, right? The data privacy and governance. Let's talk about that as the first one, because security becomes critical in these environment. Yeah, this is the one. Okay. Right? Security becomes this. Although we need to understand from a security angle about how do you basically define policy enforcement. I discussed in the earlier section that policies are being generated and defined globally from a cloud perspective, but it is applied into the edge devices through your fog node. But how does policy enforcement applies into individual devices while retaining your privacy is still a big challenge, right? So those data residency model calculation, how do you define your privacy preserving techniques while deploying those policies? That's one of the biggest challenge from a data privacy and governance perspective. Similarly, from a security lens, you still have to define how does authentication is done in a secure manner. We discussed that we can enable authentication at devices from a fog layer perspective, but then it is not standardized yet in the market. There are no controls specific for the fog node devices. So we have to come up and define a very specific model and references for fog architecture, just like we have for cloud and traditional data center environment. Okay. Now, resource management, if I talk about resource management, this is where we discussed about that you have to define and orchestrate the layers and multiple edge devices. So all those kind of things, right? How do we deciding where basically where we are to put that workload, when it is not performing, where to move it, how to move it, and if we are receiving queries from let's say thousands of edge devices, how do we load balance are still challenges. There are models and structure which is defined and fog layers handles that, but there are no defined algorithms to do that automatically. So that's another area which is being right now for design. Okay. Hope that gives some more clarity, right? Okay. Uh, I see one. Sorry, I see one more question coming from Hardik. Can we consider firewalls as fog devices? Absolutely. As I said, right, all these end devices like firewalls, gateways can be considered as fog devices if there are certain kind of analytics being done. And the modern firewalls, the next gen firewalls brings that capability with you. Okay, so yes, you can consider them as fog devices, but you have to put it in the context of how these are being defined in your environment. Okay, any further questions?
Thank you, sir. And once again, now thank you for being with us and generously sharing your expertise and starting from the fundamentals to the industry insights of for computing. Um, Again, this is possible because Dr. Meenakshi ma'am, she approached and she in EY, and through her, we got you here. Thank you so much.
Yeah. No worries. Thanks a lot. And just if I summarize, right, if there is one key takeaway from you for today is basically that fog computing is not about adding any other layer, but about placing intelligence where it makes most sense, right? And as educators, researchers, practitioners, the real value is around architectural thinking, understanding where decision should happen and why. Right. And then I thank all of you once again for your time and participation. I know it's late in the day as well. Truly appreciate the opportunity to be part of this faculty development program. With that, I'll hand it back to the organizing committee, and thanks for all that. Thank you.
Thank you very much.
Ma'am, feedback link is not accessible. This sending a request. Kindly make it accessible, ma'am.
Yes, sir. Yes, sir. We'll just do it right away. For the benefit of other participants as well, the feedback link has been shared in the WhatsApp group. Kindly note that it will be active only till 9:30. You're requested to complete the feedback form by that time. Also, just to bring to your knowledge that we will be sharing one more template related to feedback tomorrow. This is the template which is required by the ATAL. So kindly give a feedback for the FDP. Keep the template, using the template, keep the feedback ready. We'll share a Google form on the last day of the FDP, and you can upload the feedback using that Google form. We'll share a drive link on the Google form and you can upload the template there. So we'll be sharing the template tomorrow. After tomorrow's session, we'll be sharing the feedback template. So kindly download the template and fill the template and keep it ready. So thank you again, dear participants. Thank you very much and have a good night. We'll meet tomorrow at 6.
Kindly,
Yes, sir.
ma'am,
Ma'am,
kindly
please
make
check
it
your link.
accessible.
The link is asking for admin rights.
Yes, ma'am.
Yes, sir.
Feedback
I
link.
will make, yeah, it'll be done right away, sir.
Yeah, ma'am, I'm waiting.
Okay, okay. Thank you, sir.